We're going to do some chemistry stations in order to learn a little bit of basic chemistry. It's a lot more interesting than just going through a lecture. So let's start at station 1. You should pick a spot, if you're not already in the back, at the lab tables back there where you see the sign for station 1. Here we're looking at atoms and what atoms are made out of. Again, we've talked about this before. An atom is the basic unit of an element. The nucleus is the center of an atom. This picture up at the top right corner really isn't correct in what atoms look like, but it's what you might think of when you hear the word atom, because you see this image a lot. The nucleus would be this reddish center, and why it's not completely accurate, there's many reasons, but one is because there's two different subatomic particles located in there. You should see protons, positively charged subatomic particles in the nucleus, and we abbreviate it P+. And you should also see some neutrons in there. Subatomic particle in the nucleus with no charge, N0 is how we abbreviate it. So there are two different kinds of molecules located in this nucleus, and different amounts of each depending on which element we're looking at. Around the nucleus we have the electron cloud, and that's represented out here by these black lines with the little brown circles rotating around. The electron cloud is where we find electrons. An electron is a subatomic particle around the nucleus located in the electron cloud, and we abbreviate it E negative or E minus. When we take two or more atoms and put them together, we get a molecule. A chemical bond is what holds a molecule together. A little bit later we'll look at the different kinds of chemical bonds, just very briefly, ionic, covalent, and hydrogen, but those names might ring a bell with you, and just know that those are the things that hold molecules together. At station 1, you're going to practice drawing atoms. Kind of. You're going to model them using some little what are called pom-poms, and then the piece of paper that's sitting out at the station in front of you. And after you model it, then you're going to draw what your model looks like in your note packet. Some things you need to know before we start. If you're looking at the periodic table, so this is for lithium. The atomic number is the corner number up here, number 3. Lithium has 3 protons and 3 electrons. Thinking about charges, why do you think there are 3 protons and 3 electrons? Hopefully you said that they balance each other out. So lithium, as an element by itself here, is stable. It's not charged, it's not positive, it's not negative, it's neutral. Which subatomic particle is missing? So we know that lithium, and we'll use this to make an example drawing, has 3 protons and 3 electrons. Which one is missing? Neutrons. So down here we have the atomic mass, and we're going to round up. So this will be 7 instead of 6.94. And what we do to find how many neutrons there are, we take 7 minus 3. The reason why, if you're interested, neutrons and protons are the only 2 subatomic particles that have mass. They have enough mass or weight to actually calculate it. Electrons barely have any mass at all, so they do not contribute to this number. So we can take 7 minus 3 and find how many neutrons there are. In lithium, we have 4 neutrons. So now what I'm going to do not draw this one, this is just an example, is walk you through making what's called a Bohr model of lithium. And I'll come back to this in a second. You're going to see me in a live video doing this, and then you're going to do the same for boron and fluorine, and then draw what you create on your page. Just as I mentioned before, the number 3 here is going to tell us that lithium has 3 protons and also 3 electrons. Because it's a neutral atom, they're going to balance each other out. To get the number of neutrons, we round this up, 7 minus 3, so we have 4 neutrons in this model. Now, you're not drawing this one out, so you shouldn't be doing this on your page. This is just an example. You're going to have 2 examples of your own to do after this one is done. So, to model, the protons and the neutrons are both, remember, in the nucleus. Now, this circle center is not the nucleus. These are where the electrons are going to be. They're either going to be on this ring or on this one. So, our nucleus is going to be in the center. You're going to use these pom-poms to model lithium. So, 3 protons. Pink is protons, so I'm going to take 3 pink pom-poms and put them in the center here. and then neutrons are green. So here's 4 neutrons, and just to save space, I'm going to kind of stack them up here. So there's the nucleus of our atom. Now the electrons line up in a certain way. Every time you have these, so when you are doing these models on your own, the first ring can only hold 2 electrons, so 2 maximum will fit here. The second ring can only hold 8 electrons max. So here we have 3 electrons, and we're going to use the white pom-poms. That means our first 2 go on this ring, and I could put them anywhere, I just chose to put them there. And then our third one goes on this outer ring. Now let's say I had a different element with more electrons. Let's say I had 6 electrons. I would still put 2 here, and then I go 3, 4, 5, 6, and I'd spread them out. And this just means that it can hold a max of 8. It doesn't have 8 in it right now. So this is our model of lithium. And in your notes, the next thing, you have a box. Now again, don't do this. You'll do this with your examples later. But in your notes you have a box, and so when you're done modeling it with the pom-poms, you're going to draw out a diagram of what it looks like for me. So lithium, I'm going to make a little key here. A dark circle is a proton, an open circle is a neutron, and let's say a striped circle is an electron. So to draw my model, I have 3 protons, 1, 2, 3, and 4 neutrons, 1, 2, 3, 4. In my first ring I have 2 electrons, and in my second ring I have only 1. So that's how you're going to draw it in your notes. So then you would clear this off and then look at the next example. So the 2 that are in your notes that you'll be doing, the first one you're going to do is you're going to model boron. So remember, this will tell you how many protons and electrons there are. You're going to round this number, and since this is 5 or higher here, you're going to round it up to 11 minus 5 to get the number of neutrons. Model it out with the pom-poms, then draw it on your sheet. Then you have one more to do for fluorine. A little bit different here. Figure it out, model it, draw it on your sheet. If you get stuck, make sure you ask me for help and I can walk you through it. Station 2, we're going to look at pH, how acidic or basic something is. Hopefully you've seen the pH scale before. And for pH, anything from 0 to 6 is considered an acid. The lower the number, so the closer to 0 we are, the stronger the acid is. Gastric acid is in your stomach, very, very strong. Lemon juice, orange juice, etc. Number 7, right in the middle, is something that is neutral. So pure water is neither acidic nor basic, and that's why it hangs out in the middle. 8 to 14 would be basic. The higher we get, the closer to 14, the stronger the base. So bleach is a very strong base. Ammonia would be up here as well. And you can also see what else fits on this scale. Look up other things online if you're interested. You can see where different liquids fall. pH has tested something called litmus paper. So at this point you should be at station number 2, and you should see some little containers that say litmus paper. You have red and blue and a couple different solutions. What you're going to do, listen to my instructions all the way through first before doing this, and then you can come back if you need to. You're going to pick a solution. There's a variety there. Pick whichever one you want. Take the red litmus paper and dip it in. If it turns blue, it's a base. Take the blue paper, dip it in. If it turns red, it's an acid. You don't need to keep it in there too long. Just a quick little dip will do. If you do this with both papers and red turns blue and blue turns red, then you have a neutral solution. So for each solution you need to test both red and blue paper. Then repeat with a second solution, a new piece of red paper, a new piece of blue litmus paper. Just throw the other pieces in the garbage and then write down on your paper what's going on as directed in your note packet. Station 3, we're looking at solutions. A solution is when you have a solute dissolved in a solvent. So for example, salt water. The solute is what gets dissolved. That would be the salt. The solvent is what does the dissolving. In this case, it's the water. Together you have a solution called salt water. At this station, we're going to be looking at eggs that I've dissolved away the shells in different types of solution and see what happens. So we need a little bit of background because I'm going to have you do a little bit of critical thinking. We can describe solutions in a variety of ways. We have some special words. A solution that is hypertonic. Think of the word hyper means if you're hyper, you have more energy than usual. A hypertonic solution has more stuff dissolved in it. This is always in comparison to something that is hypotonic. A hypodermic needle goes under your skin. So the word hypo means less than, under, that kind of thing. A hypotonic solution doesn't have as much stuff dissolved in it. So look at the beaker to the left. The little stars are things that are in the solution. So let's pretend this is salt water and the stars represent salt, and then this white part here represents water. The inside, I just colored it gray so you can see the difference here. There's only one salt molecule and then this gray water. So, looking at this, the outside is hypertonic because there's more salt, more stars, than there are inside. The inside is hypotonic. Now, something fancy about water is that it likes to go where there's more stuff, where there's more solute. So, water is going to get drawn out of the egg, if this was an egg, and the egg would shrivel in this case if you put it in something that is very, very hypertonic. Let's look at another solution here. We said hyper and hypo before. Here's a different word, isotonic. Looking at the picture, what do you think isotonic means? Hopefully you said it means that it's equal. In an isotonic solution, there's the same amount of stuff dissolved outside the cell or the egg or whatever we're looking at as there is inside. So here, 2 pieces of salt in the water, 2 pieces inside. Water will move in and out of the egg equally. So if you're looking at the eggs back there and you don't see a change from the control egg, the one that I didn't do anything to, and compare it to one in solution, they look like they're the same size, the egg is probably in an isotonic solution. Our last option is to have the outside of the cell or the egg or whatever we're looking at be hypotonic. So out here, there's only one salt molecule, whereas inside the egg or cell or whatever we're looking at has 3. It's hypertonic. It has more stuff dissolved in it. And like I told you before, water goes where there's more stuff. Solute sucks. So the water's getting sucked where there's more solute. In this case, if this was an egg, what would happen to the egg? The water would actually go in it, and it would get bigger. So if you see an egg that is huge compared to another egg that's sitting out there, then this is the kind of situation you're looking at. So at this station, I dissolved the shell away from a raw egg by soaking it in vinegar for 2 days. So the eggs in the beakers are completely raw. If you touch them, like if you were to throw them, they would break and be a mess. They are not hard-boiled. They are completely raw. There's a membrane that's holding it together still. You need to look at the egg that has not been treated. It still has its shell on, it's the control, it's sitting out next to the beakers, so you can see what the normal size egg is. Compare that to the eggs in the beakers and decide, have they grown in size? Are they bigger? Are they smaller? Or are they about the same size? The solutions are different, so they should all look different. Using what you see and what we just talked about here in these 3 situations, decide, is each egg sitting in a hypertonic, an isotonic, or a hypotonic solution, and explain. If you're confused, don't guess. Please call me over and ask, and I'll help walk you through at least one of the examples, and then have you figure out the other one on your own. And as I said, please do not touch the eggs because they are very fragile and it takes 2 days to soak them in vinegar and get rid of the shells, and so I will not, if you broke it today, have the chance to get ready for another 3 days to set this up for people who need this experiment, so please be very, very careful. So take a look in your note packet, see what's coming up next, and as always, if you have any questions, let me know.